So firstly, thank you so much, Hamza, for the introduction as well. I would say there is so much going on in this carbon capture industry that we are very often flooded with the information on projects, technologies, as well as the different regulations. And basically, if someone is finding it difficult to navigate through these challenges or if there is, or if you are someone who is just starting, you have just started exploring this field, then I think this seminar is the correct place for you. Good morning once again, and good afternoon, depending upon the geographies. I am Parikshit, and today I will be giving you a sneak peek into the entire CCUS landscape, and so that you would understand it from an industry perspective. So before we dive in to the actual presentation, it is equally important for me to understand what exactly interests you the most. Is it the technology part, or is it the basically it's about the job perspective, something like this? And that's the reason, if there is something that you would like me to incorporate during the presentation, if there is something apart more than what I just mentioned, then you're ready, or you can feel free to just type it in the chat so that I can take it during the presentation part. So with this, I would just start with the presentation. Um, so what I would suggest is we'll be going with this outline. I would give you a background regarding how exactly is the CCUS landscape, how was it, how is it now, and what are the further steps that are required. Secondly, we would be looking at market potential. Where exactly is it foreseen that the major CCS implementations would be there? What are the different technologies and pathways for this CCUS? Then the job opportunities part, which is as far as the chemical engineers are considered, there that is the most crucial part. In addition to the technologies part, when the technical part is done, then it is equally important how exactly we could build a profile so that we could have a impactful career in this field. And this presentation would conclude based on different technologies as well as the job perspective. So to start with, we can see a very interesting graph on the right hand side, wherein we see the emissions, CO2 emissions through time. What we see here is the CO2 emissions on a timeline from 1950 to 2020. And it is clearly visible that the CO2 emissions have grown sixfold from the perspective from 1950 range to approximately current scenario, which is 2022. If we just look at different countries, or if we look at different regions, it is very clearly visible that, okay, the CO2 trends are more or less closely related to the industrial growth. So we can see that more or less the EU and European Union as well as US had one of the major emissions, or one of the were major emitters in from 1970s to approximately 1990s or 2000s. However, there are developing countries who have just recently started in 1990s. We can just take an example of China, which has started in late 80s to just explode in the emissions, and that is expected to peak in 2040. So it's like different countries have different roadmaps because there is a history to it. Huh? So we can't change the history, but what we can change is what happens next. Okay, and that's where the different pledges or different roadmaps come into play. When we talk about roadmaps, this is a very interesting graph wherein we can see what are the global emissions. Okay, and again on the timeline. So what happens if we don't do anything? That is typically termed as a business as usual scenario. Okay, and we can clearly see that if we don't do anything, the based on our current policies, the global emissions are going to explode, and they are nowhere going to go near net zero. So typically, what is the most I would say famous pathway, that is a 1.5 degree Celsius pathway, which typically means that we need to restrict the global rise in temperature to approximately 1.5 degrees Celsius. And then based on that, the other technologies or the other policies needs to be designed around it. So this was one of the major thing that we have to keep in mind, that there have been different commitments, there have been different pledges and targets. So each and every different scenarios are more or less going towards the net zero. But again, it is important that even with the most optimistic target, it is very likely that we would be missing 1.5 degrees Celsius target. From a chemical engineering point of view, this is the typical roadmap that everyone should be aware about, that okay, there are different pathways, and we would be checking what are the different technologies that we need to implement to kind of reach these goals. Next part is when we always talk about CO2, 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 and it is important to know there are also other gases or emissions that are even more. They have a higher potential of damaging our ozone layer as compared to CO2. But just because CO2 is very much prevalent in the industrial landscape, it is the CO2 that we talk about when we kind of talk about the emissions. So it is more or less the CO2 that we talk about. And once we have noted that, okay, it is the greenhouse gas, specifically CO2, that we have to target, that we have to mitigate over a period of time, then it is important where exactly does this CO2 comes into play. Okay, so on the right hand side, we would be able to see different industries which are the major emitters. For example, let's say 40% of the CO2 typically comes from power industry, which could be a power, gas powered, or the oil fired plants. No? Then again, it's like
semester free registration.
again, it's like it relates to the different transport field or also the building industry. Luckily, I come from a building industry, which is basically the cement industry. Cement industry is one of the major emitters of CO2. That also means there is a very high potential of CO2 mitigation in this field. And based on this, I would be able to give you a very nice perspective with regards to what could be different CO2 pathways that have to be implemented in cement industry.
Sorry to interrupt, Parikshit. Can I kindly ask everyone to mute themselves during the presentation? That would be a great help. Thank you. Yep. Sorry, Parikshit. Yeah, please continue.
Okay. So this was more or less about, okay, which is the greenhouse gas that we need to target, and on the right hand side we see that which are the industries that we need to target when it comes to the mitigation part. Next, once we know that this is the greenhouse gas and the industries are well known, what is important is what is a typical roadmap. So since I said that I come from cement industry or the building material industry, this is the tentative roadmap which is given by SEM Bureau. And here what we see is a graph of CO2 emissions against the timeline. So what we see typically is that these are the different decarbonization levers that are typically foreseen in a cement industry. Again, everything starts from business as usual case. If we see that, okay, the top part, the current CO2 emissions from the cement industry is approximately 2.5 to 3 gigatons of CO2 per year. And if we continue with the current situation, then they are going to explode, because again, there have been significant production in cement production, and the rise of cement and steel are not going to back down in couple of multiple years to come. So if we don't do anything, it would be the CO2 emissions are going to explode. Now it depends what are the different decarbonization levers, or what are the measures foreseen to just reduce the CO2 emissions. And here we see different measures that have been listed. For example, efficiency in design and construction, efficiency in concrete production, which is basically again the milling operations, or it could also relate to the savings in cement and binders, what kind of materials we are using in cement, if we could use a better a substitute in cement which are less CO2 intensive, or again savings in the clinker production. So typically cement comes from a clinker, approximately 90-95% of cement is clinker. And typically when we talk about cement plants, they are basically clinker production plant, which is a kind of pre-product of the cement. And again, what we see here, that all these decarbonization measures that we see, they are contributing. But with these decarbonization measures, are we able to reach a net zero? No. So there is a need for a significant step, and that we foresee in CCUS, which is one of the major measure that has to be implemented in the industry to reach the climate goals, or the individual country goals, or the region goals of achieving the net zero. Here we could see that the carbon capture CCUS could tentatively contribute to 36% of the for reducing the CO2 emissions. So it is important to see that, okay, CCUS, which was initially kind of good to have option, has become a must have option in the cement industry as far as the CO2 roadmap is considered. Moving on to the next part, here is a very brief overview about how exactly the CCUS looks like. If someone has already deep dive into this particular field, then he would be knowing that, okay, there are different sources of CO2. typically there are two major sources. One is the diffused source, which means CO2 that we see in the environment that is around us or the air. And it is called diffuse source because the CO2 concentration is minimum. It's like approximately 300 to 400 ppms. And another source is a point source. So when we come to the point source is basically the industrial sources of CO2. And here we find CO2 in percentage per asset area, which is basically 5% to 30% when we come across this stack area. Stack area is the at the end of the process in, let's say, cement plant, power plants. Here we typically have 5 to 30% of CO2 on a dry basis. So what we see is it depends from where exactly we would like to remove CO2. Is it a diffuse source or is it a point source? And based on these, the carbon capture technologies are implemented. Again, once the technologies are implemented, what we get is again either a liquid, most probably it's a liquid CO2. It could also be a gaseous CO2. So then it comes to the transportation part. There are different modes of transportation that we would be seeing in detail. And then we get an option, okay, should we go for the storage or should we go for the utilization part? This depends clearly on the business case in a particular region. So it is highly possible that if in one area the utilization business case is not that much economically viable, the same case could be viable in areas where there is a different geography or the labor rates or in general the weather. No? So what we would be doing, we would be looking at each and every stages, three major stages, basically the capture technologies, transportation, as well as storage and utilization. So we would be looking at these stages one by one, starting with obviously the capture technologies. When we look at capture technologies, it's currently there would be a lot of technologies. So don't worry, I'm not going to go into each and every technology. Otherwise, it's a very comprehensive topic, and that we can speak for hours on this topic. What I would be doing is I would just give you an overview about what are the different technologies, and then we would be looking at what is typically implemented in industry based on the maturity level of different technologies. So if we look at CO2 separation processes, that is more or less this is what we learn in heat transfer or mass transfer subjects as a part of chemical engineering program, which is the absorption. It could be a physical absorption, it could be a chemical absorption. Then again, adsorption processes wherein there is a pressure swing adsorption, there is a temperature swing adsorption. So again, there is a chemical adsorption and physical adsorption. So it's like adsorption processes, membrane processes, cryogenic processes, and biological processes. Now, typically, what we foresee is, as of now, it is important in the selection of technologies, which technology is at the higher maturity level. So as far as business are concerned, it would make less sense that, okay, we are implementing a technology which is not, which is at a lab scale, and then we are taking directly to the industrial scale. So that is something that typically doesn't happen. It is not a kind of viable scenario as far as a business case is concerned. So typically what we have to focus on is how mature is the technology, okay, or how commercial is the technology, so that we would have lesser risks when we are implementing such a technology. So when we go ahead in this regards, we see, okay, what kind of technologies are there. Here we see the TRL is the technological readiness level on the left hand side, and on the right hand side it's a description about what exactly does these levels mean. Okay, so typically if we are at a lower technological readiness level, which means these technologies are at lab scale or a pilot scale, which could not be implemented directly on a huge scale commercial scale basis. When we go to the higher technologies or higher level of TRL, technological readiness level, then we see that, okay, something or the pilot technologies have been tested, okay, and they have been tested in a relevant atmosphere. So it can't be like, okay, I have tested this technology in power plant, so I could take it for granted, then this would be applicable in cement as well. So this is not something that is typically done. If the technology has to be, the technology has to be implemented in a relevant atmosphere and or a relevant environment, and then based on that it is upscaled to the different industries or the kilns. Then what we see is typically the post combustion and pre combustion processes, or these technologies are the technologies which are at a higher technological readiness level. So what are typically post-combustion capture technologies? These technologies we have already seen. Post-combustion means once the combustion has taken place, typically these technologies or carbon removals or carbon capture measures are implemented at the downstream part of a plant, which means once the flue gas has been treated, it has been cooled down, it is just before the flue gas is sent to stack, we remove a part of the flue gas and then we treat it. Okay, this typically happens after combustion, so it is called post combustion capture. And typically it's like adsorption technologies that are implemented as far as the post combustion capture technologies are concerned. So it need not be restricted to only these technologies. There are still different technologies. Even the membrane is implemented downstream. Again, it depends upon the impurities that we have in gas. And based on that, these technologies are implemented after combustion. Okay, because typically CO2 would be released after combustion. So it makes sense that we implement these technologies after combustion. So these post-combustion technologies are having one of the highest technological readiness level. So if someone is looking for, let's say, I would like to implement it very soon, let's say in 5 years or so, then these are quite lucrative options. Then there is something called pre-combustion, which is quite famous in integrated coal-fired power plants, as well as the natural gas fire plant. So this is something that these technologies are implemented before we go into the turbine. Even both these technologies have been implemented since a long time, so they are quite mature technologies. What is not very matured or it is at a nascent stages is oxy-fuel combustion. So I've been working on oxy-fuel combustion technology since 4 to 5 years. We are into the implementation stage of this technology. Again, so what we are building is a prototype. So there are different projects wherein a prototype is underway for the oxy-fuel combustion. And the what we can see is more or less these three technologies that we are seeing are based on the point source. Point source is the industrial capture, okay, wherein we have high CO2 in percentage areas, 5%, 30%, 80%, something like this. What is used for the diffused CO2 source is typically the direct air capture, wherein we can take in air with approximately 400 ppm of CO2 and then we can treat it. So that is typically done in a direct capture. So this was an overview about what are the different types of technologies that have been implemented. What is important to understand, okay, this is an overview. Let's dive deep into individual technologies. Again, what I have selected is a technology which is a post-combustion capture technology, which is quite prevalent in different industries as of now. And what we would be looking at is I would like to give an overview from an industrial perspective based on what are the ongoing industrial projects so that you get an idea, okay, how exactly that is implemented. So coming to the post-combustion absorption-based CO2 capture is what we see again is this is based on a solvent absorption process. So what happens here, we see that a flue gas, which is basically taken towards from the downstream part of the plant just before it is sent to stack, or more or less a major proportion of the dust in the flue gas is removed, we get our flue gas. So this is the raw gas that we have. Initially, what is done, typically what we have is this CO2 gas or the flue gas is having approximately 100 to 150 to 200 degrees Celsius, depending upon from which point this is taken. So it is important that we cool down this gas. Initially, what happens inside the carbon capture system is a pre-treatment part, wherein we cool down the gas and that is sent to the absorption tower. So this cooler, it could be of different types. It could be a quench cooler wherein we just circulate in a counter current flow with a cooling water, or it could be a heat exchanger, coil heat exchanger. But typically what is used is a quench tower. So in this regard, what we would have is a flue gas that is cooled down and then it is sent to the absorption column. Now what happens is in the absorption column, we have a solution which is absorbent, and that solution is sent from top to bottom, and our gas goes from bottom to top, and they have a counter current exchange. And what happens, because of the affinities of CO2 molecules towards the solvent, this CO2 molecules are just trapped in the solvent. This solvent goes to the pump, and from this pump it is sent to the desorption column. So what happens in the desorption, again the solvent is heated, and just because the CO2 that has been captured in the solvent is sometimes chemically bound to this particular solvent. It has to be heated, and based on this reboiling heat, the CO2 is released. So what is important to understand is many a times we have learned this particular absorption processes in our chemical engineering curriculum. What is important is what are the different types of solution that is used. Okay, how much solution has to be used, and selection of solution based on how much percentage of CO2 is there in the flue gas. So that is crucial. Again, what is crucial is the amount of energy that we have to put in this. So in the entire process, what we have is we have to put in a significant amount of energy in the reboiling so that we can boil out the CO2 that has been captured in our solvent. So here what happens, the solvent, the CO2 is released, that is sent to the condenser, and then it is captured further. What is important is with this process, we require a significant thermal energy, and that is more or less given in this particular dissolver portion. It's around about 70 to 80% of the thermal energy that is required for the entire process is given in the desorption column. Now, typically as chemical engineers, what we have to understand is whenever we look at these processes, we have to consider an overall perspective about how much energy that we have to put in, whether it is a thermal or whether it is an electrical energy. And then based on that, we calculate the performance of the system. Again, what depends is to improve the performance of the system. It is important that, okay, how exactly is the energy getting kind of exchanged in this process? And that's the reason there is always the kind of heat integration that happens. So a portion of this rich solution is sent to the heat exchanger, that is again kind of preheated, so that we would have to we would have to put in less reboiling heat into this particular column. What is typically used in as a solvent here is, or a solution here is basically amines. Amines are very widely used. They have been used in different oil and gas industries. But what we have to make sure that our amines very much safe as far as the scaling effect is concerned. What happens is there is many a time, because of impurities that are inside this flue gas, there is a contamination of amines, and then we have to take care of the part that we have to remove from our loop. So again, there is a significant headache involved as far as the post treatment of amines is considered. Then moving on to the next part, what is the technological readiness level that we have discussed? That okay, this post-combustion absorption based capture is again at a higher technological readiness level. What can be achieved is 90 to 95% of the capture rate can be achieved. So basically, if you have, let's say, 100 kg per hours in the incoming flue gas, then 90-95% means the 90 to 95 kg per hours can be removed from the initial flue gas that is sent to the carbon capture unit. The purities can be achieved, that is again on the wet basis, which means the flue gas or the CO2 rich flue gas would be having a high concentration of CO2, but also moisture. So what is typically possible is 90 to 98%, which means it is again not a food grade product. What happens if we need a food grade product? Then we need to implement further technologies to enrich it further. What we get at the end of this process is the gas phase. Okay, when we have to transport, typically the transport happens in the liquid phase. So again, we have to understand that, okay, even if we have captured, let's say, 95% of the CO2 that we have sent in, and even if we have reached 98% of the purity, it is important that our flue gas would need further treatment if we have to go for a storage perspective. Because again, for storage, we need significant amount of purity based on the off takers. As far as this post-combustion absorption process is considered, one of the major implementation is happening in Norcem cement plant in Brevik. Okay, so this I would like to give just an overview about how exactly it looks like. On the right hand side, you can see a cement plant, and we can see how exactly they have modified the cement plant with the help of a video to see how exactly this particular technology is implemented here. So we can see different columns that have been there in this particular part. So typically we see these two columns that are there. Again, absorption, desorption processes. what they have done is they have taken a part of the flue gas and they have sent to this acre carbon capture technology that they have implemented, and the purified CO2 gas is then sent to the compression station. The moisture is removed and then it is stored. Now, once that is stored, then it is sent for the further storage inside the saline aquifers that we would be seeing at a later stage. What is important that we as chemical engineers should always keep ourselves informed with regards to what are the key players for this particular technology. So typically is Aker Solution, Carbon Clean, Shell, MHI. There are also new players that are coming into the field. So it is important to keep, okay, what are the difference between these technologies and how exactly these technologies could fit in a particular industry. Now, this was about the absorption process. Absorption process, which I mentioned, is again a post-combustion capture process, and it is at a higher technological readiness level. So the next part that we are going to see is a membrane-based process. Membrane-based process is something that membrane-based process is something that we are seeing that has been recently implemented. Again, it is not at a very high technological readiness level, but again, what we see is it clearly depends upon how is the business case, what is the capex, and what is the opex for this particular plant. What this membrane processes are again driven based on the permeation rates of individual components. What we see is again the flue gas that we have that is typically taken in. Again, as I said, is what this flue gas requires is a pre-treatment. No? If that has to be temperature regulated, the dust has to be removed. You understand, it's like in cement plants, we have significant amount of dust that is in the flue gases, and therefore it is quite crucial that we remove this dust before that is sent to membranes, so that to avoid choking. No? So if our flue gas is at, let's say, 200 degrees Celsius, 150 degrees Celsius, then that has to be cooled down, let's say 30-40 degrees Celsius, depending upon what kind of membranes that we are using. Again, what happens is flue gas is sent to the membranes, and based on the permeation rates or the permeability of the membrane, basically the performance of the membrane, we see the selective absorption or the selective permeation of CO2 over the membrane to varying degrees, and based on that, the first degree of separation occurs. So what happens afterwards? It's not like that a single membrane would be able to reach, let's say, 90% of the purity, 99% of the purity. For that, it has to have a very huge pressure differential, okay? Because that is again is pressure driven. Whenever we say pressure driven it means that we have to implement a significant amount of compressors or the blowers so that we reach that delta P. Again, what I mentioned is this is a modular concept. No chemicals are required, and it requires a little bit water as far as the pre-treatment is concerned. But there are no major equipment that could be critical. As of now, what we have seen is, again, this is the first stage of separation that occurs. What is CO2 rich flue gas that is sent to a dryer kind of thing? Because again, sometimes what happens is moisture gets carried away via membranes depending upon what is the pore size, and then therefore it is important to remove the water. Again, what happens is this moisture reduced flue gas, which is CO2 rich, is sent to the second stage, or again it is sent to a compressor wherein it goes to the CO2 purification section. What is CO2 purification section is? It is highly crucial that before we go into the CO2 purification section, it could be a rectification part, that water is removed, otherwise you would be getting solid particles in the rectification section. And that's the reason you'd always see a drying part, which could be a TSA cycle, which is a temperature swing adsorption cycle, before we go to the cryogenic part. In the cryogenic part, what is typically removed is inert gases. So when we come to CO2 recycle, what happens is inert gases are typically which is not CO2. No? So that is nitrogen, oxygen that is removed in the rectification part that is sent to membranes. So it goes into the second loop of recycle, so that we can leach out maximum amount of CO2 that is remaining in our flue gases. So this is a typical major loop that we see as far as the membrane is considered, this one. And the minor loop is basically the CO2 lean flue gas is sent to another membrane. Again, it depends upon the what kind of CO2 concentrations that we have in our flue gas, and based on that, if we have some remaining CO2 in this particular section, that is again leached out and sent back to this particular inlet, so that we can have a enrichment of CO2 at the initial stage. So what is left is a treated flue gas, which is sent again to stack. This gas is typically checked with regards to impurities, so that we can check what could be the further implications as far as the impurities are concerned. Then with regards to membrane capture processes, one of the company that is going strong with this technology is MTR capture. MTR capture is typically US based technology, which have been implementing this full scale capture at a dry fog station plant. What we have seen is, again, this is a medium technological readiness level, 6 to 7. Capture rate that can be achieved is 70 to 90%, which is the capture rate. Purity is again 85 to 90%. So it's not like a particular anyone would be able to say, okay, this is something that you would be achieving at any cost. It depends upon the modular concept. It depends upon what kind of membranes you are using, and again, what happens at the downstream part of the CO2 treatment. So is it used for a capture, or is it used for a storage part? So typically, what is it used for capture, or is it used for a use case? So typically what happens is, the end purity is typically determined by the CO2 off-takers. And if they say, okay, they need a food grade, then membrane standalone won't be sufficient to reach a food grade purity. So what we have seen until now is we have looked at two different post-combustion capture processes. Initially, amines, okay, basically the not amines are majorly used in this post-combustion solvent-based capture. These technologies that are at a higher readiness level, which is they are commercially available. And the second that we have seen is the membrane-based capture. So this is not very commercially available, but still, in, let's say, as far as the landscape of 2030 to 2040 is concerned, it is quite likely possible that this brick could be used as a pre-concentration step. So if we look at a situation wherein we are given food grade purity as our target, we can easily see that we won't be able to reach with any one of these two technologies. And that's where the final concentration or the final treatment of CO2 comes into play. That is the cryogenic separation. So there are different players as far as cryogenic separation is considered. Important is the feed gas here is should have a purity of, let's say, minimum 85 to 90%. Okay, so it doesn't make any sense to implement a very expensive cryogenic processes at the start of our process, wherein we have, let's say, 5 to 30% of the flue gas concentration, because firstly, it is a high pressure process. When it comes to high pressure, as I mentioned, it involves significant compressor energy. So it doesn't make any sense to involve this particular cryogenic separation at the start of any capture concept. So typically what happens is this separation takes place based on the condensation and sublimation properties of the gas. What we have is the feed gas that is initially there is a dehydrator, or again, what I said is a dryer based on typically temperature swing adsorption processes. And this feed gas, which has moisture in ppm areas, that is sent to the separator, which could be a kind of Joule-Thomson effect triggered separation. It could also be a rectification column based on what is the concentration at the start of the flue gas. No? So what happens here is it is cooled, it is sent to the Joule-Thomson expansion device, and then it is sent to the rectification. Here again we have a reboiling part, okay, which boils out the CO2, which boils out the inert gases, and that is these inert gases are sent back to the compressors. So these inert gases are basically O2 and N2. We have to understand that the concept of post-combustion absorption process is different as compared to the cryogenic separation here. Here, what we do is we remove the inert gases and cool down the CO2 in such a way that this cool down CO2 is then in a liquid phase, and it is sent back via a heat exchanger, so that this cold CO2 can give up a part of its heat, a part of its cold to the incoming feed gases. So typically what happens is incoming feed gases are hot, and if we employ such kind of energy integration or heat integration, then we have to spend less energy as far as the cryogenic separation is considered. What is different is the capture rates. So in we can reach as high as 99.99% capture rates, and a very high purity is achievable in the cryogenic separation. That indeed comes at a cost. So it's not like it's energy efficient process. But again, if this process is implemented at a later stage of the enrichment, then it makes sense. It is not something that is implemented at the start of a process where we have 5 to 30% of CO2 gases, CO2 concentration. So a typical players is Air Liquide, Air Products, Linde. There are new products like Chart or something. They are also, but they are kind of limited to a particular geographies. So as a chemical engineer, we have to look for different technologies that are there. What are the technological uh, partners that they work with, and based on that proceed with the implementation part. Now, here is basically an overview about what are the different pathways that we have discussed. Is we discussed about post-combustion solvent, we discussed about this membrane, we discussed about the cryogenic capture. So here it is quite easily, here it's an overview about what are the capture rates achievable in solvent capture, standalone membranes, cryogenic captures that we have discussed. It is important to bifurcate, okay, how much energy that we are putting into a entire process. So whether it is a thermal or whether it is an electrical energy that we put in. So these are the typical numbers that we foresee in the industry with regards to the energy requirement of a particular process. And what is important is you can see that no single technology can reach a high pure grade of CO2 product, which means no single technology, if let's say post combustion capture is implemented, no single technology can do it on an individual basis. So there always has to be a combination of different technologies to reach a end purity. Okay, which basically means, and that is the beauty of the entire process, because a chemical engineer has to understand, okay, what is the current concentration of flue gases and where exactly we have to reach, what is the business case, and based on that we have to select a technology which is which is a combination of energetically most efficient processes. So that's the beauty of the entire process, I would say, and that is something that a chemical engineer should find challenging as well as interesting in a way. So this was about the KPIs, key performance indicators of different separation technologies. Now, once it is captured, what is important is how exactly that could be sent, that could be transported. Again, there are different ways, different transport methods. It could be a pipeline, it could be ship, truck, and rails. What we typically see is these rail cars or trucks have similar range of conditions. Okay, these conditions typically dictate how exactly you would be designing the entire capture process, or more specifically how you would be designing the cryogenic part or the end part of the process. Okay, because then you have to make sure that, okay, your CO2 is liquid and it is at approximately 20 bar, and between -20 to -30 degrees Celsius. Okay, so if it has to be sent via pipelines, then we see that both phases are a possible, vapor phase and dense phase, but the conditions are quite different. We are at significantly high pressure and significantly high temperature as far as the pipeline are considered. As far as the technological readiness levels are considered, pipelines are quite expensive. There have been different studies which mention that, okay, this makes sense when we have a transport more than 1,500 kilometers. Again, it depends upon region to region. What we have typically seen in the industry is trucks are something that are not used on an industrial scale, because again, there is an issue with the restriction in size. Okay, we can't have, let's say, 100 200 trucks every day. That would be logistically difficult. So typically what happens in industries is, if an industry is near a port, then it is usually it opts the ship transport route. If it is inside inland, then it is typically the rail transport that is used, or these are typically the rail transport that takes a priority as far as the economic perspective is considered. As far as the pipelines are considered, it is more or less in US that they have more than 50 years of commercial experience in pipelines, and that have already been used for the transport of CO2. As far as Europe is considered, the focus is more on repurposing the pipelines which have already been used for the natural gas treatment or natural gas transport pipelines. So it is very important to see difference in different geographies and what is the approach. This is a very interesting project. Many of the students or people who are already kind of accustomed or they have seen this Northern Lights project, then they must be having knowledge regarding this. This is basically the same project that I showed initially when I showed a video of implementation of post-combustion capture in cement plant. What happens is it's the same cement plant that we see here. It is stored on shore, and then since it is on very near to the port, CO2 carrier ships are basically implemented. These carrier ships take the CO2 and they send it to a intermediate storage. Intermediate storage is then responsible for reaching a particular condition of, let's say, temperature and pressure, that so that it would be suitable to be injected inside the aquifers, saline aquifers. So in this video, it would be quite clear how exactly this process takes place in a graphical sense. So this is that intermediate storage or terminal. Okay, good. So what we have seen right now is basically we have typically capture site. Okay, since if that capture site is close to the port, then we could have a ship transport. What happens in the ship transport? They store it at a intermediate storage, so that this is the final step in the sense of adjusting the process conditions before the um, CO2 is sent to the subsea level. Okay, and once these process conditions are reached, it is pumped in insulated or uninsulated pipelines in a single phase bed, that is liquid CO2, and then that is sent to the reservoirs deep, let's say 2 to 3 kilometers inside undersea. Okay, and this is quite crucial as far as how exactly or what kind of licenses are foreseen for different companies. We can see that more or less the North Sea has become a quite a hotbed as far as the capture of CO2 is considered, and you would see different news that okay, more and more companies are buying licenses for the storage of CO2 there. Now, this was more or less about the transport. What is important is to understand how exactly is CO2 stored. There are quite interesting views or counter views. Okay, what would happen if the CO2 comes out? When would it come out? So typically what happens is there is an injection well, okay, that we can see here. I would suggest that let's focus on the left part first. What we see is there is an injection well always, okay. In the initial graph, that's this point. Okay, there is an injection well beneath this particular station, which is sending CO2 inside. This injection well makes sure that it is the CO2 is sent to such a rock formation, which is a sandstone rock. What happens? Sandstone rocks are typically porous rocks wherein CO2 can move freely, and such a formation is selected such that we have a sandstone rock, which is in this case is a Johansson formation, and layer is selected in such a way that we have a cap rock above it. What is a cap rock? Cap rock is typically a clay stone layer, which is, or basically a clay sand layer, which is quite thick in such a way that it won't allow CO2 to pass through it. So we can see that this yellow orange areas is something that would be a sandstone layer wherein CO2 can move depending upon how high levels they are. It is not a typical case that all the layers are in one level because of different geological formations. But there is always a cap rock which basically caps the entire level so that there won't be any leakage of CO2 in this particular process. So this is typical as far as the Northern Lights projects are considered, or the projects that are more or less into the saline aquifers level. This was an overview about what we saw, different technologies. transport part as well as the storage part, what we see is it is very important what is the end CO2 purity. As I said, that it depends upon different CO2 off-takers, how exactly do they specify a product purity. Okay, we can see that one of the product purity is just from this Northern Lights. What they have specified is CO2 purity as high as 99.81%. And what you can see is the impurities that are literally in ppm areas. Okay, some of the impurities could also be in ppb areas, parts per billion ranges. So it is important that it is not only about the main components, whereas for example CO2, O2 or N2, which are in percentage areas, but it is also about all the other components like ammonia, amines, formaldehyde, mercury, etc., that are typically even in ppb levels. For example, mercury has to be in ppb levels. These levels are decided by experts which are more or less researching on the material integrity of different storage tanks or storage ships, and based on that they devise this particular specification so that we would have less contamination as far as the CO2 transport is considered. So this clearly defines that the end purity would dictate what kind of processes we implement in the upstream plants. If we just look at different indicative costs and ranges, we can see that, okay, what is it typically happens as far as cost is considered with respect to CO2 compression, dehydration. We could see that what happens in the transportation of pipelines, again, it is a very broad range depending upon how much kilometer you're transporting the pipelines or transporting the CO2 in the pipelines. More or less, long story short, it is important to see the ranges. For example, if the compression, which means once we capture CO2, if compression takes, let's say, 20 to 30 US dollars per tons of CO2, and then there is also the transport via different pipelines or ships that takes, let's say, again, additional 20 to 30 USD per tons of CO2. We have to calculate the total cost, and still even after transporting there are some charges, for example CO2 injection, storage, as well as the monitoring charges. So roundabout, even if there are technologies wherein which can say 70 to 80 euros or dollars per tons of CO2, there is something involved in addition to these carbon technologies, and that in total could go to approximately 100 to 120 US dollars per tons of CO2 if we just sum all these steps that happens even after the carbon capture. So it's not like just by calculating a carbon capture price we would be able to calculate the price of the entire value chain. More or less what we have to do is to calculate the entire price, which could be double the price, or it could be equal to the price of the CO2 capture. So let's say if the CO2 capture is 60 to 80 euros per tons, and we could have a equal more or less equal price range for the next steps. So this was about the storage part. About the utilization part, it depends upon different geographies. What we have is typically, I've mentioned that we have CO2 from different sources. We go into the capture processes, and then based on these capture processes, there are different routes. For example, mineralization routes, wherein this captured CO2 is just pumped into the concrete so that they would be stored inside these building materials. This is one of the quite sought after utilization pathway that is implemented. Hydroloom, I think that it's a company in US. They are very strongly into this particular technology. The thing is, it is important that we look what are the different pathways are there. For example, one is this CO2 mineralization, when we put CO2 or we inject CO2 inside the concrete or the fluid part of the concrete. Another way is to make e-fuels or chemicals. Another way is EOR, is enhanced oil recovery. What is important is what is the CCU lifetime. Okay, once we make, let's say, a e-fuel, or let's say we use it for hydrocarbon recovery, it is important to check what is the CCU lifetime. So if it is again coming into the loop after, let's say, a couple of days or couple of years, then we have to think, okay, how sustainable is that particular pathway. So with regards to different technologies or with regards to different pathways, as far as CCU or utilization is concerned, we can see that more or less it has been used as food packaging. CO2 has been very prevalently used in industry as industrial gases, in agriculture field, in food packaging, enhanced oil recovery. This is the part that US is a leader in. They have been using CO2 as for enhanced oil recovery since a long time. They have operational experience of more than 50 years for this particular CCU application. What is also used in as a utilization case is beverage industry or carbonization of CO2 basically inside the drinks. And for these particular food grade CO2 is considered. So again, when we talk about a food grade CO2, it is important that it would have a very high purity levels. So these purity levels would then govern what kind of technologies that we would be implemented. The reason I was saying that CCU business case depends upon geography is when we look at these algae-based biodiesels or usual algae production based on CO2, then it heavily depends upon what kind of weather we look at. If we look at these implementations typically require a hot weather. So like in Algeria or something, there is a CCU implementation for algae production because CO2 in the gas can help or accelerate the growth of algae for the production of algae. So that is again a use case wherein they try to sell dried algae on the market and achieve a financial feasibility. So these are different cases. As far as trends are considered, we can see that as far as US geography is considered, they are more or less into pilot or semi-industrial scale plants until 2030. And it is highly possible that beyond 2030 to 2035, the industrial scale plants might pick up. So what we see as far as EU geography is considered, there are already some semi-industrial scale plants that are very near to completion and they are expected to be operational by 2030. Beyond 2030, we could see a sudden jump in number of industrial scale plants that would be in operation. As far as what I see is US would be focusing on extension of existing network and more or less on EOR. There are also some use cases for CCU utilization case. What EU would be focusing on is the transport case because in US we have seen that they already have experience as far as the CO2 transport is concerned. That's not the case in EU. So that could be a bottleneck. Again, it's a chicken and egg game. Should carbon capture technologies or the partners should implement in the or should invest in the capture technologies or should the infrastructure providers, for example, should the storage be available first or should the CO2 be available first? So it's again a chicken and egg problem that people keep on going in the same loops. As far as India is concerned, we have seen that there are some small scale plants and there could be and feasibility studies until 2030. What I see is cement and power industry would be main focus because there have been funding in these fields in India. A significant difference is what we see that in EU, the industry is more or less going towards the storage area. On the other hand, India could go towards the CCU because we have seen that there are a couple of fundings available in India, more or less directed to the cement areas where there is a strong focus on CCU. So with regards to job perspective, there are three different points. I would say, firstly, it's about the industries. Secondly, it's about technology providers. And thirdly, it's about the technology builders. Okay. So when it comes to the job perspective, as far as industries are considered, then it is very highly possible that these technologies are implemented in cement industry, power industry, steel industry, and lime industry. So if someone would like to take a plunge into this particular sector, then these are the industry that everyone has to kind of track as far as the jobs are considered. Here, it is more or less about the technological providers, which are basically the license providers. Now, some of these companies are also having engineering and construction divisions. So initially we talked about Eco carbon capture, which is more or less a post-combustion capture, ExxonMobil. So here we can see different industries or the different technology providers. So that is the second aspect. It is highly likely that you would also see a lot of companies which are towards the startup part of the technologies which are at lower technological readiness level. So that also could be an interesting proposition. So what we have to look at is firstly the sectors. Secondly, it's about technology providers. What kind of technologies they are providing, at which level are these technologies? And thirdly, it's about the technology implementation part. So technology implementation is more or less done by the engineering companies. Let's say there are Petrofac. There is SIPEM. These companies are then involved in the implementation of the technologies part, which is basically the detail engineering part. Huh? So as far as the job prospects are considered, then more or less one has to consider what are the industries that would be more or less focusing on this implementation of technology, and what are the technology providers and who are the technology implementers. So with regards to prospect, or basically the profile building part, what are the different profiles that we have typically foreseen? As far as chemical engineers are considered, it is more or less towards the process design part. Okay, so which means here process design means on the technology provider part, where we devise a technology, we see okay, what is the energy consumption of the technology and how we can optimize it. Okay, pilot operators are more or less chemical engineers, engineering role, wherein you get to operate a pilot plant, research on it, do a data analysis on it, etc. Again, what we see is simulation engineers, wherein these also go towards a technology provider as well as technology implementation areas, wherein we have to simulate entire process. We have to make sure that it is incorporated in a feasibility study. So these are the core areas wherein we as chemical engineers should look out for as far as the job prospects are considered. Then is the research part. So there have been different institutes which are researching on, let's say, solution, which are researching on membranes. So again, there is a scope, but this goes more towards the chemistry part. And as far as chemical engineering part is considered, then it goes more towards the simulation as well as the pilot scale studies part. Um, then what when we go to the managerial side, then it is more or less about the project managers that has to get involved, analysts, as well as then environmental expert, which is then sustainability experts, footprint calculations, as well as LC expert. As far as these experts are considered, more or less it could go towards the consulting areas as well, wherein we have to check okay, what kind of technologies are available, which means technology scouting, how these technologies could be implemented in these cement plants. So important is there is no single solution, that it would always be a combination of technologies that we have already seen. So it is quite crucial that we have a very strong understanding of how exactly the technology functions and which technology could be implemented in which particular scenario. This was in short about what are the different prospects. In addition to this, it is important that it is not focused mainly or mostly on technical part. It typically the CCUS job roles also involve quite a multidisciplinary idea about how exactly the storage functions, as well as the transportation part. So with this, it's like I would like to summarize as far as the utilization pathways, storage pathways, and the capture pathways are considered. Um, Initially, it's not like that, okay, as I mentioned that initially CCUS was a good to have factor. Now it has become a must have decarbonization lever or decarbonization measure across all the roadmaps across industries. Okay. Another important thing that we saw today is rather than one standalone technology, it would be a combination of different technology. Let's say membrane plus cryogenics, membrane plus let's say it could be a combination of absorption plus cryogenics or pre-concentration. It could also be simply absorption and then again a drying technology. So it depends what is the use case, what is basically the CO2 specification that has been given to us. As far as the technologies are considered, post-combustion capture technologies are retrofit option, which might look favorable during initial stages. At a later stage, there could be a very strong heat integration that might needs to be done as far as post-combustion capture technologies are considered. Again, there has to be a uniform regulations from the policymakers, and as well as robust funding would be necessary from the governmental agencies, because in the early 2000, let's say 2008 to 2014, we have seen that there have been a buzz about CCUS, but because of different areas, for example, let's say funding crunch or policies, it couldn't lift off in the more or less coal fire plants in Germany. So again, it has to be, one needs to look at what are the current policies, what are the regulations before we go into the CCUS part. But as of now, it looks quite promising. This was more or less in a nutshell about how exactly a CCUS value chain functions. Overall, as a chemical engineer and climate enthusiast, we have to understand that CCUS has already taken a center stage, and we have a crucial role to play towards the implementation part. And yeah, that's what would be important. So I think this was in a short about what we discussed until now. Before we jump into Q&A section, if you have any questions, you can just put in the chat, or we can open the group for discussions. But before we jump into that, if you are interested to build a profile in this sector, or if you are interested in some technical discussions, we have a technical discussion group, which is basically the climate networkers group. I think some of the members are already here in the chat I've seen, and it would be interesting if you would like to have some technical discussions as well as build profile in this sector. Then feel free to ping me on the LinkedIn. This is a QR code as far as LinkedIn concerned, and then I would send you an invite to the group. So with this, I will give it back to Hamza. Hamza, maybe you have some words, questions, or we can open the round for discussion.
Yes, well, thank you so very much, Parikshit, for the great presentation. Thank you so very much. So yeah, I guess we can move ahead to the Q&A. If anyone have any questions, feel free to unmute yourself and you can ask them now.
Hello, Parikshit. Arpit here. So my question is, as you talked about the amines in the post-combustion capture.
Yeah.
So as we know, there are some like environmental impacts of amines also. So what about if we I know I research into so many companies into this field, and now some of the companies are using hot potassium carbonate also in this technology instead of amines. So what are your views on this?
So basically, amines, typically what has happened is many industries have been skeptical about the implementation of amines because there have been issues with the scaling part, or there is something called a formation of HSS, which is heat stable salts. So that's the reason people have been apprehensive about the implementation of amines. So therefore, there you would see that in different research projects, they don't test one single solvent. Okay, they test multiple solvents. So just to see, okay, in at which degrees of mixing we would be having less problem as far as the post combustion treatment of these solvents are considered. Coming to your question regarding HPC, so as far as the current trends are like, there are solvents who they claim that there would be less environmentally damaging, and HPC looks, which is hot potassium carbonate, looks as a quite a potential to this particular, which is quite positive as far as this solvent capture is considered. But again, what you have to look at is it's not only about the solvent. So you have to look at the complete process. When it comes to the complete process, it's about OPEX, CAPEX, and the basically the regulatory part. So this about a solvent, it more or less comes to the what is the post treatment that is required for these particular solvents. Okay, so that's where in this particular bucket I would rate HPC better as compared to amines, because they have less potential to form these heat stable salts. But again, what we have to do is there is another aspect as well, how efficient they are, and that doesn't depend on solvent, that depends upon the heat integration of the entire process. Okay, so let's say if amine technology has a particular energy consumption, thermal energy consumption, that then we have to look at, okay, what happens in the HPC process, or in the post combustion process of HPC. Is it completely thermal? Is it a combination of thermal or electricity? So that would be interesting. But purely from the solvent perspective, as of now, HPC looks much better as far as amine is considered.
Okay, thanks for your answer. And secondly, as we talked about the membrane capture also, so as I've seen on your slides that okay, it has like maximum of 80%, I would say, right? You
Yeah,
have mentioned like
so it's like it depends what kind of or how many steps that you are reaching.
exactly, yeah.
So let's say if I put multiple membranes, then I might be able to reach 90% of the recovery. Okay,
Mm-hmm.
it depends upon what kind of membranes you are using, what are the impurities in that. So if you have high SOx and NOx levels, then it is quite highly possible that after some time you'll have to replace membrane every time. So for as far as membranes are considered, it is more or less on the capex part. Huh?
Okay. Yeah.
So that was the background regarding 80 to 90%, I think.
Okay. So yeah,
Mhm.
thanks for your nice presentation and uh, your very detailed answers on that,
Thank you, Ashok.
Parikshit.
Thank you. Does anyone else have any other question you might like to ask?
Hello, Parikshit.
Yeah.
So I have just one question related to like in the post-combustion technology, like we are using the as a feed, we are using the flue gas to capture the CO2 from the flue gas.
Mhm.
So if in the CO2, like if we have the presence of sulfur, SO2,
Mhm.
because it's coming from the cement industries, or you can say like, so is it viable? Means is it necessary to remove first SO2 from the system before it enters into the absorption column, or we can get rid of in the absorption column?
See, absolutely. That's the reason. Typically, what happens before we reach the absorption column, SO2 impurity has to be removed more or less completely. Okay. So that's where these coolers come into play. And that's the reason I said, okay, initially we use quench coolers, because in quench coolers, depending upon what kind of SO2 impurities or in general acidic impurities, it also relates to NH3 impurities that we have, these have to be removed before we go into the absorption column. Okay, and for that particular part, we have to use these quench towers, which is again a kind of cylindrical column that is used in a such a way that there is a counter current flow of water, or we mix it with a basic solution, which could be NaOH.
NOH, yeah. Hmm.
So typically NaOH is used in industry, which is then able to reach approximately 95 to 98% of SOx removal. Okay. But
Hmm.
what happens is, again, SO2 is not the only sulfuric component that we have in the flue gases. That also relates to H2S, SO3. And typically it is very difficult to measure these components and the flue gas itself, because what happens at the end or the towards the stack in the flue gases in the cement industry, the flue gas, if we cool down the flue gas, then it is saturated with water. Okay, so it's like, just imagine measuring something in a saturated flue gas. So it is quite difficult, and the measurements are not very accurate. Besides, it is difficult to measure the bifurcation between SO2 and SO3. So typically what happens is, the measurement campaigns more or less focus on sulfur equivalent, SO2 equivalent, and then they design the loop or this NaOH loop in such a way that it would be able to reduce 98 to 90 or 95 to 98% of the SOx. But yeah, to answer your question, that has to be removed before we go into the absorption
Absorption column.
columns. Yeah, absolutely.
Yeah, because what is it's currently I'm working on this only in my thesis. Like I'm having the two-stage absorption system with the resorption system.
Mhm.
So currently means I have not considered SO2 in the flue gas, but
Mhm.
if something comes up in SO2, so just I want to know that yeah, we can have a quenching column or something like that.
Yeah.
One
Absolutely. So
pre-scrubber.
in majority of the cases, SO2 shall come up, because again, it depends upon what is the source.
Yes,
Typically,
correct.
coal, if the coal is used, then SO2 would be there. Sometimes SO2, as far as cement industry is considered, that also comes from the raw meal, raw
Raw
material.
meal. Yes, correct.
So there it would be there. So it would be, I think, crucial to consider that as well, because that would be a big assumption if we say, okay, SO2 is not there. So yeah.
And the one that is coming out from exhaust gas from the absorption column, so there may be the possibility, as we are not achieving 100% CO2 capture, so there may be some possibility that we have some presence of MEA, means if we are using the amine as a solvent.
Mhm.
So as the MEA solvent is not, it's harmful for the atmosphere that we can't throw it into the atmosphere. So do we suggest that we should have some post scrubber that we can remove, we can recycle back, we can extract the amine and we can reuse back into our system.
See, typically what happens is in the absorption column, you have demesters at the top. So
Correct.
majority of the things are already removed, but there could be traces of amines in that. And that's where the specifications of CO2 come into play. Okay. Or I would say emission measurements come into play. If depending upon different geographies, that is allowed in the this flue gas or the exhaust to stack. So this gas is not something that we are removing it as a product. Okay.
Yeah,
So this goes to the stack. This is returned back, and if that depends upon what kind of regulations are there based upon different geographies,
geographies. Yeah,
wherein they say, okay, let's say 30 milligrams per cubic meters of amines or something similar limit is there in the flue gases, then it should be below that. Okay, but typically what we have seen is uh, it is not a significant portion that goes into this exhaust gas. If it is goes, then it would be a very significant loss. You have to replenish the solvent very often. So every step or every measure is taken that we have minimum losses here, and if these goes to the stack, then it depends upon what are the levels that are foreseen in the stack. um, the points, there could be a requirement, but typically I have not seen, as of now I have not seen that a significant post combustion is required, post treatment is required for this exhaust gas. Post treatment could be required for the solvent in general as far as amine is considered, because that degrades. But the exhaust gas, as of now I have not seen.
and what about like means if we are using the one stage absorption and desorption system, and instead of if we are using the two-stage absorption system and desorption system, so would it be helpful like to have a more capture percentage of the CO2, or it would be like the same one only?
See, it depends. It's not like it depends upon the number of stages in the absorption column. Okay, and
Correct.
what is the inlet concentration of CO2? So if the CO2 concentration is low, so there might be stages requirement, but these stages could be incorporated in one single column.
Column, yes, true.
Yeah.
Correct. Correct.
So that's the situation.
Okay. Got it. Okay. Yeah. Thank you so
So
much.
typically, this modularization functions in membranes, because then it is step by step going ahead in the downstream processes. So as far as membranes are considered, then it is stepwise. Let's say in the first step, one is able to reach, let's say, 60% of the enrichment or 60% of recovery, then it is modularized. But typically, as far as absorption desorption is concerned, it is more or less in a single column that we foresee different stages.
Correct. Got it. Okay. Yeah.
But
Thank you.
means if you would like to discuss these projects, then means you are most welcome in the discussion groups. We look at different academic projects wherein we discuss what are the bottlenecks, and we kind of mentor students based on that.
Yeah, yeah, we can do that. No issues. Yeah. Sure. Thank you.
Yeah, welcome.
Hey Parikshit, as we talked about the quenching towers, I just had a random question in my mind.
Yeah.
Is like in quenching tower, like we are basically cooling our flue gas with the help of water, right? And then
Mhm.
water and CO2 has a tendency to react together to form carbonic acids.
Mhm.
So that might not be good for our quenching tower, right? But okay, as you said, okay, we use like NaOH, for example, to take out the SO2s and
Mhm.
NOx basically. So and CO2 can react with that also to form uh, carbonates, sodium carbonates, something like that, right? So according to you, like okay, so then we have acidic and basic something, right? After reacting with the CO2. So
Mhm.
what which will gonna react first, like which has a tendency to react with the CO2, because if water reacts with the CO2, then it's not good for our system, right?
Mhm.
So what's your views on that?
So basically, it depends upon the solubilities, no? So here we have to look at what kind of solubilities that we have, because if we lose a lot of CO2 in the water itself, which is typically taken out, then it won't make sense as
I
far as the
understand.
option is considered. So typically, what happens is a very marginal portion of CO2 gets converted into that, goes with the water. Majority of the SOx are then carried away with the basic part, because SO2 has higher tendencies to react And that's the reason we see SOX are more or less removed, let's say 98% in the water based on what we implement as a basic component. So NaOH could be used as a basic component. It's a mixture, let's say 40 to 50% of NaOH is used in typically in the quench tower, and that majorly removes the SOx. So CO2 is not a thing that is that goes significantly towards the formation of carbonic acid. So it depends upon what are the selectivities, huh? And
Okay.
so the affinity is more towards the removal of SO2. So a very marginal amount of CO2 goes into the water.
Okay. Thank you.
Welcome, welcome.